Assalamu alaikum, bismillahirrahmanirrahim. Hello dear students, this is my lecture 2 which was related to uh, development lens. Okay, so in first lecture I will give you a complete kind of explanation about bond, that what is bond, what factors affect the bond, how bond mechanism occurs, how you can say tension transfer from concrete to the steel. Okay, so I explain them in full detail. Okay, and in today's topics I am going to explain you about development lens. Remember, whenever we are, you can say, designing a reinforced concrete beam, uh, we we use a term Fy. Okay, Fy, that is the yielding strength or yielding stress of steel. Okay, so one of the most, you can say, important questions which you can say which creates in mind, that how much length is necessary, how much length is necessary, you can say compulsory, of the reinforcement bar which can be embedded, which can be inserted into the concrete to develop that yielding stress. Okay, this is a very important question. Okay, which must be handled in this topic over here. Okay, for example, if I will explain them graphically, uh, let's suppose I have a beam, uh, 3D over here. Okay, this is beam 3D over here. Okay, uh, this is beam 3D over here. Okay, and I design, steel bars in this beam. And let's say I design one bar for this beam and for a certain loading. Then I design this beam at a yielding stress of this steel. Okay, that is Fy. Uh, we are taking it 60 ksi or 40 ksi. Okay, let's say this is 60 ksi. If I design this steel through its yielding stress, that is 60 ksi. Now the one of the most important which you can say, which is right over here, that how much length is necessary to insert of this bar in this beam tube, you can say, in this beam, that it will give me the yielding stress equals to 60 ksi. Okay, that how much length I will insert in this beam. Okay, in this beam, how much length. Okay, either I have to need to insert whole length in this beam, or either I have to insert a portion of this length. Okay, because when the concrete is cracked, when the concrete is cracked, so this insertion length become reduced. Okay, this insertion length become reduced, and it doesn't give you that yielding strength then. Okay, so the length which is necessary, which is compulsory, to embed, to insert in this concrete beam to develop that yielding stress, is called development length. That is the development length. Development length वो लेंथ होती है किसी भी reinforcement बार की, जो किसी कंक्रीट के अंदर हम प्रोवाइड करते हैं ताकि हमें 60 के साथ, यानी जिस स्टील की स्ट्रेस पे हमने जो डिजाइन किया है वो डिजाइन स्ट्रेस हमें डेवलप कर सके। ये लेंथ जो बेसिकली होती है, फॉर एग्जांपल if it is let's say if it is 20 feet length, span length, and I design the development length that LD, it is denoted by LD, and I design it that it is 5 feet. This 5 feet means 5 feet development length means that the this steel bar length for a distance of 5 feet must be inserted into this concrete to develop that yielding stress at which you are designed that beam. Okay? It is very important. If you don't provide this 5 feet length, your design stress of that steel would not be developed. Okay, and as a result, your beam will be bent, will be failed, anything will happen. Okay, so development in from that point of view, it is very important. As a civil engineer, you must know about the development length, and you must know about the. So you see that this is a kind of definition. If we come to Nelson book, you will see the definition of development length. The preceding discussion suggests the concept of development length. As we explain about bond, so from that bond point of view, we must know about the development length. Okay, we must know about the development length, that how much length is necessary to develop, to insert into the concrete, to embed into the concrete, that it give me the desired bond strength which transfer that tension of concrete to the steel. Okay, so that definition, the development length is defined as that length of embedment. Okay, necessary. Embedment means to insert. Okay, to insert into the concrete, necessary to develop the full tensile strength of the bar, controlled by either pull out और splitting. यानी कि ना तो splitting हो और ना जो है वो pull out हो, ना तो splitting हो ना तो pull out हो, ठीक है ना. उसके बगैर कितनी लेंथ आपको दरकार है कि ताकि आपकी जो फुल टेंसाइल स्ट्रेंथ जो है, जिस स्ट्रेंथ के ऊपर you are going to design your member. Okay, that may be yielding, that may be any stress. Okay, with reference to the moment, and therefore the steel stress evidently, this is a kind of splitting. I will explain these terms. Okay, and you see that, for example, this is a kind of example which is given right over here. Okay, let's say this is a simply supported beam over here, and it is subjected to loading. Okay, so you see if A is the point with reference to the moment, and therefore the steel is evidently maximum at point A, neglecting the weight of the beam and zero at the supports. If the bar stress is Fs at A, then the total tension force AB in Fs must be transferred from the bar to the concrete in the distance L by bond forces. Okay, to fully develop the strength of the bar AB equal the distance R. This means that this means that what this paragraph means. This is a kind of example. You have a simply supported beam which is subjected to point loading over here. The maximum bending will be, if you draw the movement diagram, I think so it will be like this kind of thing. Okay, so this is a 1 degree curve. Okay, so 1 degree, second degree, 1 degree, sorry, this is a 1 degree and this is 0 degree. Okay, so this is the region, this shaded portion is the region, where the maximum bending will be occurred. Now if this region, there is the maximum movement. Okay, so basically this means that at the maximum movement which is developed over here at this point A. Okay, so for example, the tension force which is developed over this point in both directions, let's say if the stress in the steel is Fs. Okay, steel stress is equal to Fs. So, and the bar area is equal to A B. Okay. So the total tension which is developed in this bar, the total tension which is developed in this bar will be equals to P is equal to Fs into area of bar. This is your tension. Okay? This is your tension. So this tension will be at both sides. Okay. So this means that how much this length. Now it says that this length should be such that this length L should be such that the tension in this steel developed will be equals to FSAB over this length, over this length. ओके अब ये टेंशन जो है बेसिकली ASAB है, ठीक है। अब ये लेंथ जो है बेसिकली इतनी होनी चाहिए, इतनी लेंथ होनी चाहिए जिसमें बॉन्डिंग की वजह से जो बॉन्ड फोर्सेस जो है उसके जरिए से इतनी टेंशन प्रोड्यूस हो जाए। दिस लेंथ शुड बी सच दैट ड्यू टू फोर्सेस ऑफ बॉन्ड्स, ओके, the tensile stress, the tensile forces in this bar will be equals to this Fs into A. Now this, therefore this length is called the development length. Okay, it says if the actual length L is equal to or greater than the development length. Now if this length L equals to development length or it is greater than development length, this means no premature bond failure will occur. The failure of bond will due to the failure of the beam due to bond will not be occurred. That is one criteria which is satisfied. Okay, that criteria will be satisfied, and there will be no failure, bond failure. Okay. This will be so even if in the vicinity of cracks, local slip may have occurred over small region along the beam. It is seen that the main requirement for safety against bond failure is this: the length of the bar from any point of given steel stress Fs or at most Fy to its nearby free end must be at least equal to its development length. If this requirement is satisfied, the magnitude of the nominal flexure bond force along the beam. It is not important, but the most important thing from this paragraph, you must know about that the length of the beam which is embedded into the concrete should be greater than or should be equal to development length to develop that whole stress which is equal to Fs into the area bar. Okay, if it is not equal to that, so basically we will see that from this paragraph what we learn basically, the main theme of this paragraph you can say is that your embedded length L should be greater than or equal to development length. If this length equals to or greater than development length, it is ensured that the failure of the beam apparatus occur not due to bond failure. It may be due to shear, it may be due to bending, something like that, but it is sure that it is not due to bond failure. And the other thing which is also important from bond failure safety point of view is the length of the bar. That the length of the bar which is embedded into the concrete should be greater than or should be equal to, you can say, to the development length. If it is not, so bond failure will occur, slippage will occur, and one of the most important thing which is just mentioned in this last paragraph is also very important for us to know about. If this development length is not, it is not justified. Sometimes it happens that the length which is available right over here is not so much to give you the full development length. It is sometimes it is less. For example, if this fluid is come here, or if you calculate the development length, let's say if the distance from this point A to this face is 2 feet and your development length is 3 feet, then what you will do? You have different option over here, but Amongst them, one option is that you have to provide hook over here. Okay, you have to provide hook over here. You can provide special anchorages. Okay, and you also can decrease the bar diameter, because once you are increasing your bar diameter, your development length will increasing. Okay, and once you are decreasing your bar diameter, your development length will decreasing. So by changing the development, the bar diameter, your development length will be decreased or increased. And as well as by providing some special hooks, you will see that there in later stages of this lecture, as well as some kind of special anchorages like headed bars. You can provide them by bend ups and something like that. So many different kind of arrangements can be made to provide that development length, because this is important. Okay, so what are the factors which will affect the development length? Amongst those factors, the tensile strength of the concrete is very important. Okay, although the tensile strength of the concrete, in the calculation of the development length of concrete, or steel, or calculating for steel, you don't see the tensile strength of concrete. We relate that strength with the compressive strength, Fc prime and the root. So basically, tensile strength is that kind of strength of concrete which affect bonds, okay, and which also prevent cracking of concrete, okay. So once your cracking of concrete is, that is prevented, your bond forces will be high, will be maximum, and thus there will be no slippages, okay, of steel. So one thing is tensile strength. The other thing, which is weight of concrete, is also important, because lightweight concrete, the, the tensile strength of that concrete is less as compared to normal weight of concrete. And similarly, you can see cover distances. I already mentioned about a lot of things about this cover distances: side cover, bottom cover, center to center. These are very important from development point of view. Okay, development length point of view as well, because no cover distances affect bond stresses, and once your bond stress is affected, your development length. If your bond forces is in maximum, your development length will be minimum, and your bond stresses are minimum, your development length will be maximum. That is a direct relation between these two. So bar spacing important, cover distance important, and the one of the most important thing, that is transverse reinforcement. A very important thing, transverse reinforcement. Transverse reinforcement, you can say we provide them in our beams. Okay, if this is a beam, you will see we will design stirrups, okay, which is perpendicular to the bar, okay, to the plane of bar. Now the confinement action of these stirrups play a very vital role. Okay, a very vital role. You will see in the formula of development length, you will see the effect of these confinement. Okay, so if this spacing of these stirrups is less, your development length will be less. If it is maximum, your development length will be maximum. Okay, so it has also a direct relation with the confinement, because when there is confinement, this means there will be more bond stresses. There will be, the steel is confined, and that don't allow the steel to slip. Okay, so they produce a kind of confinement action, and due to that confinement action, you can say uh, your bar will not be uh, slippage. So this is a kind of formula you will see based on the results of statistical analysis. It is based on the statistical analysis, not it is an, you can say it is it is a it is proved, but it is based on, you can say it is you can say this is experimental formula, you can say. Okay, so you can see that development length will be is equal to 3 by 14 fs and roundabout like that. What is dv? Dv is the dia bar. Okay, cv basically it is the smaller of minimum cover, one half of bar spacing measured to the center of bar. Look, smaller of minimum cover, smaller of minimum cover, side cover or bottom cover, in which the smaller one will be taken out, okay, or one half bar spacing, one half of bar spacing. Look, half of the bar spacing, center to center of bars. KTR is what? 40 ATR divided by SN, which represent effect of confining reinforcement. I will already mention you that the confining reinforcement increases, decreases. Once you are increasing this confining reinforcement, your development net will be decreases. Okay, because there is indirect relationship. Okay, ATR is what? Area of transverse reinforcement. If you provide, for example, if you provide uh, number 3 stirrups, so you know about diameter of number 3, that is 0.11. Okay, so a STR, basically ATR, whatever they will be, that is 2 times of 0.211, that give you 0.22. Okay, 0.22. So you must know about this topic. Okay, KTR. What is KTR? ATR, basically the area of transverse reinforcement. Is the spacing of that transverse reinforcement and spacing of stirrups. In basically these are the number of main bars. Okay, number of bars developed or spliced at same location. These are the longitudinal bars or main bars uh, at which through which you provided your confined. Okay. Equation 6.3 basically captures the effects of concrete strength. Okay, because concrete strength. Okay. Uh, Concrete cover and transverse reinforcement on LD and serves as the basis of design for the full development in FS. At the later stage, we will see that we will, for example, we design in SCI code, we design for FY, not for FS. So we replace FS by FY. So that equation will be seen in something like different shape. Okay. Bars are placed in the forms during construction such that a substantial depth of concrete is placed below those bars. There is a tendency for excess water, often used in the max forward capacity, and for entrapped air to rise to the top of the concrete during consolidation. Air and water tend to accumulate on the underside of the bars. Tests have shown a significant loss in bond strength for more than 12 inches. So this means this is basically the effect, you can say, the effect of water in air. Whenever we are dealing with this equation, we are providing CD. We can say this is top reinforcement. We can say this is bottom reinforcement. जब भी हम इस फॉर्मूले के साथ डील करेंगे तो हम देखेंगे कि हमारी जो बार है वो टॉप पे है कि वो बॉटम पे है. तो अगर टॉप पे है तो उसके लिए जो है उसके लिए जो फैक्टर्स है उसके लिए कुछ फैक्टर्स है. तो उसमें यू मस्ट नो, आई विल एक्सप्लेन दिस थिंग. ओके, इसके कहने का मतलब ये है कि जब आपकी बीम की डेप्थ 12 इंचेस से बढ़ती है तो क्या होती है कि पानी और एयर जो होती हैं वो कंसोलिडेशन की वजह से जो है ना अंडर साइड ऑफ द रीइंफोर्समेंट जो होती है वहाँ पे एक्यूमुलेट हो जाती है, और एयर और वाटर जब बार के अंडर साइड एक्यूमुलेट होती है तो उसकी वजह से बांड स्ट्रेंथ बहुत हासिल होती है. ठीक है ना. तो अगर 12 इंचेस से ज़्यादा हो तो फिर हम इस इफेक्ट को whenever this depth of concrete is more than 12 inches, we must account for that effect. Okay, because it affected the strength of the concrete, because it affected the bond strength. Okay, this effect increases as the slump of the concrete increases and is greatest for bars caused near the upper surface of a concrete placement. What does it mean? Okay, I will explain you this term. Okay, in later stages. Yes, epoxy coated. In this equation, basically this is the kind of basic equation, but there are certain factors which affect that development length. That factor is your depth of your concrete section or your member, as well as the coating which is provided to the steel. If it is epoxy coated, zinc coated, so due to coating of steel, what will happen? The friction forces is lost. and due to that you can say the bond stress become decreased, and once your bond stress become decreased, this means your development then will be increases. So what that coating effect, what the depth effect, you know, as well as what is the cover effect, you know. So there are some kind of modification factor, you know, which we will introduce. And remember, there is another factor, that is the modification axis reinforcement ratio. Sometimes, basically, whenever we are designing a concrete member, so we deal with as provided and as theoretical and as provided. Basically, you calculate, let's say, a is steel. You calculate three square inches, but there are you're not able to provide the exact amount of steel 3 square inches. You have to provide more steel than 3 square inches, which is theoretically needed for that beam, that is 3 square inches. You are providing 3.10, 3.20, 3.3 square inches, okay, because there is not proper arrangement of bar you can make to provide that exact amount of steel, okay. आप practically आप बार को इस तरह सेलेक्ट नहीं कर सकते जो आपको एग्जैक्ट 3 स्क्वायर इंच स्टील दे दे। आप सेलेक्ट करते हैं एज प्रोवाइडेड, जो आप लगते हैं जो आप नंबर ऑफ बार सेलेक्ट करते हैं, नंबर ऑफ बार आप जो सेलेक्ट करते हैं, तो फॉर एग्जांपल आपको बीम के लिए थ्योरेटिकली 4 बार नीडेड है, तो आप 4 बार इस तरह डिजाइन नहीं कर सकते जो आपको एग्जैक्ट अमाउंट ऑफ स्टील दे। आप मोस्टली जब कैलकुलेशन करते हैं तो आप बार्स को राउंड करते हैं। फॉर एग्जांपल आपको थ्योरेटिकली 4.5 चाहिए, तो 4.5 बार तो आप प्रोवाइड नहीं कर सकते, आप 5 बार प्रोवाइड करते हैं। जब आप 5 बार प्रोवाइड करते हैं उसकी वजह से आपकी एसटी बढ़ जाता है। तो whenever you are increases your AST, that axis steel which you are providing here having an effect over the development length, and the length which you are calculating from that formula LD, you have to multiply this length with that steel ratio, okay? So basically this is the basic ACI base formula, okay. This is the basic formula, okay, which is used. But in most of time we will see that many factors in tension and compression affect this development length. So basically we deal in this selected paragraph, we deal those factors, that what is the effect of coating, what is the effect of axis reinforcement, what is the effect of depth of concrete is placed below those bars. So that that is, there is a very important term which says finally based on the bars with very short development lengths, most with values of LD divided by BD. Whenever we are calculating development length, we calculate them in ratio LD divided by DB, but that ratio must be less than 15, okay. It was observed that smaller diameter bars require lower, I already mentioned this, okay. This is the ACI, some kind of provision for tension. This is also ACI limitation, that LD divided by DB must be greater than or equal to 16, okay. Now we comes to the basic, this is a very important line you must note about this, that note that in any case development in LD must not be less than 12 inches. The development length of any bar, whether it is larger bar size, whether it is lower bar size, it must not be greater than 12 inches. Sorry, less than 12 inches. It must be equal to or greater than 12 inches. Okay. Now, this is the basic equation for tension. Okay. Equation for development length for bars and wires and tension. So, this is the basic ACI code. ACI code 25.4.2.3. You can see this equation in the manual. Okay, right in this manual. You can find out this equation in this manual, like chapter. You can search it and you can find it. This equation in this manual, okay. Determination of development and required for positive movement, and determination of development and required for positive movement, reinforcement and continuous. For rectangular beam subject to simple bending selection of reinforcements from Bhara. This is for bundle and this is for positive movement. So from here you can, if you search out, you can found this equation. Okay, and let us tell you people do it and search it. It is also you can also found in 2011. That is 1995, because 2005 and 2011 these codes are modified and every 3 years. So you have to know about these restrictions and these code provisions, uh, that what they basically says about development length and what kind of, because modification, and these are the bar splices. So page number 209, 209, this is the development length for tension. 209, 209, 209. Development of edit and mechanically anchored tension. इसका बनना है. So I have make a little bit for chai. Okay. So I take tea. Okay. Uh, Now I'm just right over here development and splices of reinforcement according to ACI code. So basically these are ACI manual 31811, which explain about this basic ACI formula, like over here, which is almost cutting here, but you will see the basic things like psi. These psi factors will be explained in that formula in the coming session, and you will see that what is psi t, ktr, psi t and psi e, how much its value, what is this one. Okay, so you will see the whole detail of you can learn about a lot of things about these things from this formula, from this manual. Okay, so what I basically mean that I was want that I familiar you people with the manual. Okay, so this formula basically derived from is taken out from that section of manual. This is the development. This is the basic ACI formula which work out for tension. So you will see that LD is equal to 3 by 4V FY into psi T into psi E into psi S, 4 4V and lambda into FC prime and root and something like that. Okay. So you will see that how you will explain these terms. Fy, as I already mentioned you that there is Fs which is replaced by Fy. Lambda, you will see that this is the factor which is introduced for normal weight concrete, light weight concrete. Okay, Fc prime is the compressive strength of concrete. It is a well-known term. Now, the most important thing of this equation is this one. this equation. And I think basically the importance of this is that the the topic of development that will become most tricky and most confusing one is the uh, basically this was the this was the basic factors which make this calculation most tricky, most confusing. Okay, these due to these factors, these are little bit confusing one. But one thing I will mention you, if you understand these terms, it is then very simple. It is not tricky, and it becomes very easy for you people. Okay, if you understand it completely. Okay, in which the term CV plus KTRDB may not be taken greater than 2.5. A very important restriction of ACI that this factor should not be greater than 2.5. Almost it is taken up to 1 or 1.5. Okay. In equation 6.4, the term or defined values are sin t. This is sin t. Now, the sin t basically you can say this is casting position factor. Casting position factor I will already mention you in the prior discussion that where you have to place your reinforcement, whether your reinforcement is top reinforcement or whether your reinforcement is bottom reinforcement. Okay, so that is the factor. For example, I will mention you right here that if for example if I draw, let's say I will draw a clear sketch. I search for a concrete section like this one. For example, not this one. Okay, let's see. I draw a new one. Let's say yes. For example, I think, let's say for example, I have a concrete section. Okay, this is a concrete section, and I have bars right over here. So this is bottom reinforcement. This is bottom reinforcement. And ACA code mentioned that if there is not 12-inch depth, 12-inch depth, because there is a very small depth over to the bottom. Okay? So if there is not 12-inch depth lies over here, because if there is 12-inch depth, so the water from the upper surface and air is accumulated under of this reinforcement, and that decrease the bond stress. So due to that, it has an effect of on the development line. So basically उसकी वजह से आपकी development line decrease होती है. तो अगर ये 12 इंच से ये डेप्थ कम है, ठीक है, 12 इंच से ये डेप्थ कम है, तो फिर इसको हम बॉटम रीइंफोर्समेंट कहते हैं. और बॉटम रीइंफोर्समेंट की सूरत में आपके पास साइड ही जो होता है वो 1 होता है, ठीक है ना. आपके पास साइड ही जो होती है ये आपके पास 1 होती है. लेकिन अगर ये टॉप रीइंफोर्समेंट है और उसका डिप जो है वो 12 इंच से ज़्यादा है या 12 इंच के बराबर है, तो फिर जो होगी ये जो साइड फैक्टर है 1.3. इट इज़ अ वेल नोन फैक्टर, जिसको फिर हम टॉप रीइंफोर्समेंट कहते हैं, जो कि जिस तरह कैंटिलीवर बीम में जो होता है, and like in cantilever, like in negative reinforcement in continuous beams. So in that situation you have to put this value 1.3, but in simply supported beam you have to take this side equals to 1, but depend upon the 12 inch depth. Okay, that is the side E जो है basically that is a coating factor, epoxy coating factor. Sometimes we do some kind of coating over the steel. What does it mean? That for the purpose of corrosion control basically. So in that case, if you do that coating, if your coating is epoxy coated zinc and epoxy dual coating bars or wires with cover less than 3 dB or clear spacing less than 6 dB, this is a restriction in zinc code. You do epoxy coating or zinc coating, okay, but your side cover or bottom cover less than 3 dB or clear spacing between the bars. This is the clear spacing. I already mentioned you. This is clear spacing, and this is side cover. If this is less than 6 dB, and this side cover there is R, not both. At least one should less than 3 dB or should less than 6 dB. Then you have to take this factor 1.5. And all other epoxy coated or zinc epoxy dual coated bars or wires is 1.2. Then you have for all other epoxy coated. If these criteria are not met, for example, these criteria are not met, then you have to take 1.2. Okay. So it is important. It is very important for design from design perspective. Okay. These factors are to be used. Uncoated and zinc coated galvanized. Okay. This is a very important term. Uncoated. If you don't use coating, or you use zinc coated galvanized coating, then it will be 1. However, it is very important. Psi T and psi E should not be greater than 1.7. If you multiply these two factors, psi E and psi T, the product of these two will not be greater than 1.7. It is another restriction of SA code. Okay. Psi is the size factor. You know, I already mentioned you, whenever you are increasing your bar diameter, what will happen? Your development length is increased for higher size of bars, and once you are decreasing your bar size, your development length will be decreases. So therefore, you see that once if your bar size is 6 or smaller, you have to multiply 0.8. So once you multiply 0.8, your development will be decreased, and if you multiply it with 1, so development will be remain constant. It doesn't affect. Okay, that is the lambda. Lambda factor is also because in already I mentioned you, okay, once if your concrete is normal wet concrete or light wet concrete, it affects. So for normal wet concrete, your factor is 1, but for light wet concrete, your factor is 0.75. CV, a very important term it is. Okay. Uh, Use the smaller of either the distance from the center of the bar to the nearest concrete surface or 1/2 the center to center spacing of the bar being developed. So what CV means, what is your cover? Okay. So let's see, this is very important. Use the smaller of either the distance from the center of the bar to the nearest concrete surface. Look, you have side cover, you have bottom cover, and as well you have center to center spacing between the bars. So what value you have to choose for CV? Okay, you have to choose the minimum value between amongst these three values. आपने इन तीन वैल्यू में से जो आपके पास साइड कवर होती हैं, जो आपके पास बॉटम कवर यानी साइड कवर है, बॉटम कवर है, और जो सेंटर टू सेंटर डिस्टेंस है, इसका हाफ लेना है, इसका हाफ लेना है, सेंटर टू सेंटर डिस्टेंस का हाफ लेना है. तो ये हाफ, ये और ये, इन तीनों में से जो वैल्यू मिनिमम होगी वही वैल्यू आपने सीधी लेनी है. इट इज क्वाइट सिंपल. द हाफ distance, the center to center distance between these two bars, whatever the value will be, you have to take the half value. Then you have to select this distance and you have to select this distance. But center, look, either the distance from the center of the bar to the nearest concrete, this is to the center of bar, this side cover is to the center of the bar, this bottom cover to the center of the bar, and CB may be half in between the centers lines of these bars. So you have side cover to the center, side cover to the center, to the nearest. Okay. So in तीन वैल्यू में आपने you will understand these terms in examples. Okay. but you must know a little bit knowledge about these things, that what is CV, that is you have to select this value from three terms. Okay, KTR, transverse reinforcement index, which is equal to 40 ATR SA. Okay, what is ATR? I already mentioned you. What is S? I already mentioned you. What is in? I already mentioned you. Is a simplification. The design is parametric to the KTR equals to 0. What important term? That for simplification of this formula, KTR is some time taken by the designer as equal to 0, 1, 0. The limit of 2.5 on C plus KTR divided by dB is imposed to avoid pull-out failure. Look, I already mentioned you that you have to select this value equals to 2.5. With that term taken equal to its limit 2.5, evaluation result in LD is equal to 0.03 dB FYFC5. The experimental derived limit found in earlier codes when pull-out failure controls. Note that in all other ACA code equations relating to the development and the splices of reinforcement grade 1 to C5 are not to be greater. This is another restriction, that you have to take this value equals to 100 psi, because as I explained is that simplified equation. Now this is a kind of, you can say, a tricky equation, a kind of confusing equation. Okay, so what the designer did, what the ACI did, they simplified this equation. The simplification means they make some kind of simplification for these terms. Let's see what they did basically. Okay, so what are those simplifications? You know, what are those simplifications? According to the code, they take CV plus KTR dB is set equal to 1.5 or equals to 1. Okay, this value equals to 1.5. Okay, minimum clear cover 1 in a, that equals to dB. Minimum clear spacing equals to dB. And at least the code required minimum stirrup are ties through the end. That is another restriction. That is, simplification is done on certain basis, not just only make things simple. No, these are simplification. KTR ratio, which is known as uh, transverse reinforcement index, that is equating to 1.5, and the clear cover, I already mentioned you, side cover as well as bottom cover, that will be equal to dB, minimum dB. Minimum clear spacing amongst the bars, between the bars, that will be dB, and at least the code required Stirrup's criteria. So you have to need to understand about shear design criteria. In that criteria, you know about those 6 criteria. So LD जितनी length होती है, basically this term basically means that at the end, if you have steel bars and you provided uh, transverse reinforcement along the LD. This is your LD length. This is your LD length. If this is your LD length, so basically along this length LD, these stirrups which is placed over here, their spacing must fulfill the shear criteria, which is for stirrup criteria, which is used. What are those criteria? You know about those criteria. And that criteria can be seen by you people in your shear design. Okay, so this spacing must lies in those criteria. Okay, so this is one. Okay, minimum clear cover of 1 dB and minimum clear spacing of 2 dB. Look, this 2 basically generates two cases, case 1, case 2. Okay, case 1 and case 2. These two are very important cases. In case 1, you can see that the minimum clear cover, there may be side cover and bottom cover as well, that both equals to dB, and the spacing, clear spacing between the bars equals to dB, and at least the stirrups criteria must be satisfied. This is case 1. The case 2 is that minimum clear cover that will be equal to dB, and minimum clear spacing will be equal to the distance, the clear distance amongst the bars, between two bars, you can say, between two bars. For example, if this is one bar and this is two successive bars, so the clear distance between these two must be equals to 2 dB. This is case 2, that is case 1, and that is case 2. So basically these two cases are very important, and we will use it. Okay. So for either of these common cases, it is easily confirmed from equation 6.4 that for number 7 and larger bars, LD will be this one. Now this is this is simplified, and for number 6 bars and smaller, gamma will be 0.6. In this case, lightweight concrete, this is your final value. Okay. If these restrictions on spacing are not met, then provided that code imposed minimum spacing requirements are met, the term will have a value not less than 1 rather than 1.5, whether or not transversity is used. The values given equation this are multiplied by the factor 1.5 to the 1. As if the designer accepts Bahara. Further simplification is possible for the most common condition of normal wet concrete and uncoated reinforcement. Okay, so you can make other simplification as well. These are the simplified form. This table is very important, and we will use this in examples. Okay, so this is case 1, this is case 2, and if these criteria are not met, okay, so then you have third number case. Okay, so what does it mean? This is case 1. I already mentioned you. In that case, number 6 and smaller bars, this formula will be used, and in that case, for number 7 and greater bars, this formula will be used. And case 2 is there when the second criteria is fulfilled, same as above, and for other cases when these two criteria are not fulfilled, then you have to use this criteria, this formula. Okay, so this is important. Regardless of whether development length is calculated using the basic equation, which is at the initial stage I will explain you, or the most approximate, which I already mentioned these two above table equations, development may be reduced where reinforcement and flexural member is excess. Oh, this is very important. I already mentioned you at the beginning of this topic that we have to use modification factors. Psi factors you will use, coating factors you will use placement factor, size factor. After calculating LD from these formulas are from initial stage, the basic formula which you used, what answer you will get? You have to multiply that formula. That length with this modification factor. This is a very important modification factor. If you are using axis amount of steel, the theoretical from which is required. So you have required 3 square inches and you got 3.1 square inches. So you have to take the ratio of these two and you multiply that ratio with that LD. So you will get the exact amount. But it should be remembered, it is very important that the most accurate answer for development length is achieved or can be get from this equation. This is the basic equation, and the other one are the approximate equations. So if you calculating your length from these formulas, okay, these formulas, it almost give you greater values, but the basic equation give you a little bit lower value. So if this value is greater and cannot be justified, then you have to cross check from that basic equation. But if that basic equation correct answer is justified, then you have no need to for other simplifications or for other kind of assumptions. Okay, So this is, you can say this is an example, on development length. We do this example in next lecture, inshallah. I will explain this example, and I will also search uh, other books as well. So almost development length is defined over here. Okay, this is the basic equation which relate with the bound stress. Okay, this is in McGregor book. Okay, analysis. No, we don't concern. This is the basic tension development equation. I will explain each and every component. Okay, what is psi factor and what is dV and what is LD. I mention you all these terms from Nielsen. Mm, there is nothing to new that I will explain you. Okay, that is round about that. These are the cases, case 1 and case 2, and other cases maybe developed. Okay, so in both cases you will use that formula. I will explain you. Okay, this is case 1 and case 2, but this is in millimeter. Okay, we don't have concern. This is the criteria. In first lecture I will explain you. This distance should be greater than, this is case 1. This is case 1. This should be greater than dV. The clear distance should be greater than dV, and this to the face of this bar, to the this edge, and to the face of this bar, from this face of the bar to this one. So these should be greater than dV, greater than dV. This one greater than dV. This is case 1. Okay. And what is case 2? Case 2 is that one, that the clear distance should be greater than 2V. These both center face to face distance, this is clear distance, and clear distance should be greater than 2V, and this one should be greater than dV. This is case 2. So you will see that how we can use this. This is psi factor, potent factor, size factor. I give you whole detail about these terms. Okay, axis flexion reinforcement. At the last I will explain you that you have to multiply it as provided to the edge theoretical. That is axis reinforcement ratio factor. Okay, uh, we will deal with compression, development length, compression. Inshallah, I will explain you this topic in later stages. Okay. Now we are just only concerned. We are just only concern ourselves with the tension, not with the compression. Okay. Bundle bars we don't have concern. Okay. And hook anchorages I will explain you in later stages this, but I am just searching for development length equation example, which I will do in my next lecture. Okay. So whether there is any question? Yep, I think so. There is a question for anchorage. The basic rule governing to the development of anchorage are the basis are followed. Yes, this equation is basically for development length. Okay, we will do this example as well. And if we go to MC Cormick book, so in this equation you will see what is development length criterias, all detailed like same in there's 2 books. You will see development length. What is development length? So this is the definition of development length. Okay, this is a kind of cantilever example is given, that if it is a column and if it is a cantilever beam. So although we will explain it. Okay, these examples as well as in simply supported we will explain it. Okay, we just only concern ourselves with this basic equation. This is LD by dB ratio. We mostly calculate this ratio and then we multiply dB with that term which we will get. Okay, this is the ACI. There's 3 by 40 and this is only 9 by 10. This is the only assumption. Those are the factors which I will already explain you. Okay, so there is not anything new to explain, and this is the example. Inshallah, we will do this example. Okay, so in next lecture we will do these 3 examples in full detail, and you will understand that what kind of assumptions and what kind of factors, how we use these factors and how we calculate these. So up to this limit, if you have any doubt, if you have any questions,